So the drive for innovation is pulled into arguably the most innovative place on the planet, Silicon Valley, and we're in the heart of the Silicon Valley in Santa Clara, and we're at a company that's actually one of the few that actually can look down on Intel, believe it or not, and it's a startup company, Memoir. Welcome to the Drive for Innovation. In any survey that we've done at EE Times going back years and years and years, you have 80 to 90% of the respondent engineers plan on doing their own startup at some point in their career. Now maybe at the end of the day, 5 to 10% actually do. So you guys are the 5 to 10%. What is it about you guys and your vision of the world and your knowledge of technology that's made you go down the startup path rather than work for an established company for your careers?
So I guess for my passion, I think the passion is to find a way to change the world in whatever gifts that you're given to make that happen. So the best place to be able to change the world and bring new ideas and create a lot of innovation is through the startup path.
Right. So you guys are looking at increasing the number of operations per second with your particular architecture using an algorithmic approach. Mm-hmm. Explain that.
Sure. So the problem we're trying to solve is essentially increase the number of memory operations, which really means the number of unique times you can address a memory and request data. It's a little different from memory bandwidth, which is just give me as many bits as possible. So an analogy is if you look at a hard disk and you want to read the whole sector, you can read the next 10,000 bits sequentially, and that's bandwidth, just raw amount of data in and out. What we're trying to focus is a little more intrinsic, harder problem, which is how many times can you request unique pieces of data? That's really the foundation of the problem we're trying to solve. And we call that memory operations per second.
MOPS.
Or MOPS, yeah. So we kind of coined the acronym in hindsight. But the approach we've taken is a very system-centric approach. So rather than try to make memory faster by making better transistors, and there's a certain law of diminishing returns now that most of the work, innovation has been done in the circuit space. We've applied a sort of systems perspective to it and said, gee, if you could architecturally or algorithmically make a memory faster, even though intrinsically it's still running at a slow clock speed, then what can be done? So, you wanna?
So I think with the advent of this technology, what we've been able to do is make the memory building process more of a software problem instead of a hardware physical design circuit problem.
Where are we in terms of productization? I assume it'll be an IP block, maybe, or something like that?
Yeah, today, in fact, we introduced our first product based on this technology. It's called Renesas 2X. And Renesas is because Rebirth, we're really changing the way people touching memory or implementing memory. 2x stands for 2 operations per second, not 2 operations per second yet, 2 MOPS. Later on, we'll be introducing a higher accelerated version of the Renesas. But the 2x, what's unique about 2x, in fact, if you look at the whole semiconductor ecosystem, we're able to reduce the risk, accelerate time to market, and design or produce application optimized 2-port functionality with half the cost by eliminating the need for the industry to use what's 8 transistor bit cell.
Are re-architecting a memory module itself, or just attacking the bus, the pipeline between the memory and whatever engine it's banging on?
So we take an existing memory macro as is. So we're not modifying the transistor layer. So we take it as is and then apply a CS-style algorithmic layer in front of it, right? And so what we want to say is, well, leave this as is. You have this front end, a wrapper or an IP, if you will, and then expose more ports. So even though this memory can only do 1 operation per cycle, we'll expose an interface that allows you to do 2 or 3 or 4 operations per cycle. as Adam mentioned, Renaissance 2X, the first product, is exactly 2 operations per cycle. And how we do the 2 operations, even though the memory can support only 1, is essentially a secret sauce.
So guys, talk to me, when we're out on the road, we're talking to engineers, entrepreneurs like yourselves, we're always trying to kind of burrow into that aha moment that led you down the technological path that you've gone down. What was your aha moment where you realized, well, that's a logical way to approach improving memory bandwidth?
So it took us almost, I would say, 12 months after we started Memoir to really hit that aha. And it was a bunch of, organic improvements saying, hey, I think we can do something for writes. We think we can do something for reads. But can we put it together?
Basically, we were adding 2 additional dimensions to what physical memory has now. Physical memory right now has a depth and a width. And we added the 2 extra components, which any number of read ports, any number of write ports. So that was the aha moment that basically we saw that this can be general and be applied everywhere.
So every solution is a breakthrough in some respect, but there's always a trade-off, especially in design. What's the trade-off here? Is there more overhead in programming? Is it the fact that it's a new approach?
The main trade-off we've done is really area. So what we're saying is, given your base raw material, which is a circuit, it's a 1-port memory, we'll add 10% in area or 15% area to make it 2x faster. We'll add another 15% to make it 3x faster, and so on.
Right.
So that's what we're trading off. And you're absolutely right, there's no free lunch. So a little bit more area gives you better performance. What was interesting though is that the raw material that we use, the 1-port memory, is so dense that even though you have that 15% area, it's actually better than using a circuit that does 2x intrinsically. And I think Adam can comment.
Yeah, I think even though we're adding 10-15% area overhead to make a 1-port, 2-port, the alternative is to add 100% area.
Right.
So from that perspective, we're saving area, we're saving power, and we're making our 2-port as fast as a single port. So now for the first time, the industry can focus on making single port memories from which we can then do the 2-port and the 4 ports and the 10 ports.
So you guys have a lot of experience with startups in your individual careers. How's this one different?
All startups share one thing in common, and that is the passion and the energy level. And I think that's what I really enjoy about startups. You get an opportunity to build something from scratch, and you have an opportunity to change the world for the better.
I would second what Adam was saying, that the main fun is in innovation, is in being creative. I mean, at the end of the day, if you're in a deathbed and you look back at life and what you've done, you won't feel that you created something which is of better and different from the norm, and that you did good to the world, not to use the cliche, but eventually that's what makes you happy, or satisfied, I should say. There's lots of things that make you happy, but satisfaction is a more longer term effect. And to me, Memoir at least has been a foray in essentially that. We have a very broad technology, unlike some of the stuff I was involved in previously. It's really broad across the semi space. And I think done the right way with the right team and right set of people, we can actually go beyond, being a shot in the dark, if you will.
Yeah, I think for me, I agree with Sundar. I think the previous startups that I've been a part of is they were trying to solve a niche problem, and it wasn't so general as what Memoir is providing, where we're actually going to change the entire semiconductor world on how people do ASIC design. That's the greatness about what Memoir brings to the table.